Welcome to today's webinar. The topic today is modeling and design of code-formed steel sections according to Eurocode 3 and RFEM 6. Yeah, the webinar is also valid for RSTAB 9, but we will present it in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. For instance, the Dlubal website, the German and English webinars, newsletters, and so on. I will be the moderator today and will answer your questions together with Walter. Sonja will do the presentation, but my two colleagues can introduce themselves.
Hello, I would also like to welcome you to today's webinar. My name is Sonja von Bloh and I will be the presenter today.
Hi, my name is Walter. I'm responsible for customer support and for the development in steel joints. Today I will answer you with Andreas together to your questions in the chat.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. For the attendees who participate the first time, you can show or hide the control panel with that arrow here, and then you can enter your question here, and we will answer you. If you don't get an answer during the webinar, because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email questions to info@dlubal.com. Okay, then I hand over the screen to Sonja. Sonja, it's your turn.
The topic of this webinar is the design of cold-formed cross-sections in steel design. I will design the cold-formed omega uprights of a rack, which you can see here in the image to the right. Today, I will first show you the calculation workflow and then the modeling of special cross-sections in RSECTION. In the next step, I present the structure and the loads and go into the imperfections and the combinatorics. Then I design the cold-formed cross-sections in steel design and evaluate the results. If the cold-formed cross-section is included in the cross-section library, you can use this cross-section and determine the effective cross-section in steel design. If it's a special profile, you can create this cross-section in RSECTION. In addition to the steel design add-on, the RSECTION program and the effective cross-section extension are required to determine the effective cross-section in steel design. It's also possible to determine the effective cross-section in RSECTION. However, this is not necessary for a design in steel design, but it can be used for the preliminary design. No stability design is described in the standard for double bending of non-double symmetrical cross-section or torsion. However, the standard allows a calculation according to the second-order analysis with the approach of global and local imperfections taking into account the warping torsion. In this case, only cross-section checks are required since all stability effects are covered by the calculation. The add-on required for this is warping torsion. If you want to determine the imperfection to be applied from the mode shape, the add-on structure stability would also be required. I would like to point out that the draft standard of Eurocode 3 Part 1.3 contains a new stability design for biaxial bending in combination with axial force for single symmetric cross-sections. If there is no double bending at the non-doubly symmetric cross-section or torsion, The stability design can be carried out using the methods described in the standards. In addition, cross-section checks and serviceability limit checks are also possible. Stability design checks and serviceability design checks are not implemented in steel design right now, but we are working on it. The code from Omega cross-section that I want to use as an upright is not included in the RFEM cross-section library. I therefore create this cross-section in RSECTION. For this, I open the program RSECTION first. The cross-section geometry is available as a centerline model in DXF format so that I can use the import function. So for this, I start the import about import DXF, and then I choose the corresponding DXF file and click on Open. And in the import dialog, I select the option to create elements on center lines, and here I define a thickness of 3.5 millimeter. With this import function, the part and the elements are generated automatically. Elements are required for the calculation using the thin walled analysis and for the calculation of the effective cross-section, since only then the subpanels are available. The subpanels are required for the classification and calculation of the effective cross-section. If no elements are defined, the cross-section is treated as a class 3 cross-section in the design add-ons. Furthermore, I have to select the material. Here is the material already selected that I wanted, but if this is not the case, I can select it from the material library. Then you can open this material library via this button, and then you can select the material that you want to use. Then I start the import. And the necessary part, you can see it here, is already created, and also the elements. If you click here on it, you can see the elements in yellow in the working window. I want to choose the thin walled analysis. For this, I open the base data dialog, and here I choose the analysis method thin walled analysis. As already mentioned, elements must be defined for this. This setting affects the default setting in RFEM. If necessary, I can change the analysis method in RFEM. Furthermore, I select cold formed as the manufacturing type, so that the design is carried out according to the standard for cold formed cross sections and steel design add-on. Currently, it's also necessary that the effective cross section according to EN 1993 part 1.3 is also selected here. However, this will no longer be necessary in later versions. In our section, I can also calculate the effective cross-section and the stresses. This is useful, for example, for a preliminary design. This has been demonstrated in previous webinars, so I won't go into it today. However, it makes sense to start the calculation. I do this, and maybe we can also control the generated subpanels. That's okay, and then I save this cross section. I have already created the rec in RFEM 6. For this, I open the rec in RFEM 6 now. The uprights consist of the omega cross-section I just created in R-section. I first import this into RFEM. To do this, I double-click on the uprights and then I open the cross-section library and click on From R-section. Then I choose the omega cross-section I just created in R-section. The option Thin Wall Model is activated. This setting was taken from the chosen analysis method in R-section. However, I can also deactivate this option here so that the calculation of the cross-section properties is then carried out using the finite element analysis. If this option cannot be selected, then no elements are defined in the R-section cross-section. Furthermore, the manufacturing type is set to cold formed. This setting was taken from the setting I defined in R-section for this cross-section. The special cross-section is also used as a beam. Here, these cross-sections are also created with R-section. I open such a member here. The beams are connected to the uprights with screws. The connection stiffness is represented by a rotational spring. For this, I created a hinge. I go to the top hinge and I show you the hinge now. Here a rotational hinge is defined with a spring constant. In the cross-aisle direction, the rack is stabilized by a bolted framework made of cold form C sections. I open such a member here. In order to consider the shear stiffness, longitudinal springs at the ends of the bracing members are applied. Here hinges are defined. I show you this here. And here a translational hinge is defined with a spring constant. The partial restraint of the upright base depends on the contact pressure between upright base and slab. Therefore, the rotational stiffness is to be taken into account. And here I show you the support. Here a stiffness diagram is defined for the rotational stiffness, and the rotational stiffness is not considered as a constant but as a variable that depends on the compressive force. The stiffnesses of the joints are fixtures in this example and can be determined experimentally. For example, the goods are placed by automated storage and retrieval system. The automated storage and retrieval systems is guided on a rail on the floor and on a guide rail in the rack and aisle in the racking head. The aisle bar here serves to introduce the horizontal loads into the rack. Load cases are created for the dead load. I open here the load case for the dead load. Here the checkbox active self-weight is activated so that the self-weight is automatically calculated. There's also defined a load case for the unit loads. I show you the unit loads here. The loading on the beams is assumed being distributed uniformly over the length of the beam. The unit load acts at the top of the cross-section. I show you this. So for this, an eccentricity is defined here with a reference here on the top of the cross section. In addition, another load case is created here for the automated storage and retrieval system in a horizontal direction. Here a nodal load is applied. The stability design may be carried out as a cross-section check if an analysis according to the second order theory is carried out with the approach of global and local imperfections. To take lateral torsional buckling into account, it is important that the internal forces are determined considering the warping torsion. I would like to demonstrate this on the stability design of the uprights. The uprights could also be designed with the stability designs described in the standards. As already mentioned, these have not yet been implemented but is in work. For this, I first activate the add-on torsional warping and I click here on OK. Warping at the member ends is assumed to be unhindered by default. To transfer the warping between individual members that are connected, you can define a set of members. The warping should be continuous for the uprights, and the uprights, as you can see here, consists of several members, so that at every member start and end are releases for warping. So it's necessary to define sets of members. I use a visibility to be able to quickly select the uprights. To do this, I go to the navigator views and I activate a view for members by section, and here I choose the omega section and I activate the visibility now. Now it's easy to select all the members with this cross section, and then I have to right click on a member and I choose here the function create member set. Then 12 member sets will be created. I look into one member set, and here you have the possibility to use the discontinuous torsional warping option to control whether the warping should be transferred or not. This is supposed to be transferred, so I don't check this checkbox now. Okay. Then I must define the imperfections. For this, I first create an imperfection case. So I go here in the navigator data and choose new imperfection case. I first create an imperfection case initial sway plus x. And I choose here the imperfection type local imperfections. I click on OK. I then create a new member set imperfection. For this I go to local imperfection and choose here new member set imperfection from imperfection type initial sway, definition type relative, and I define a relative initial sway of 1/500 in the direction of the global x direction. The initial sway of 1/500 is the minimum value from EN 15512. Then I have to assign the imperfection to the member sets, so I choose here all member sets and then I click on OK. for the initial sway plus y, I copy the imperfection load case I just created. To do this, I open this imperfection case and choose here copy selected imperfection case. Here I edit the name, click on OK, and then I have to modify the imperfection direction for this imperfection case to y. Okay. For the initial bow and X, I create another imperfection case. So here, new imperfection case, initial bow Y, also from imperfection type local imperfection. First, I define a visibility for the uprights. To do this, I select the uprights first, and then I choose here visibility by selected and related objects. And then I choose the wireframe model, and I want to show also the numbering. And for the cross aisle direction, I define the intersection of the diagonals as the length. So from here to here and from here to here. For this, I create a new member imperfection. So I go here, new member imperfection, from imperfection type initial bow, definition type manually relative, and for the omega cross section I use the buckling curve B, so that I define an initial bow of 1 divided by 250 in the global direction plus x. Since I'm defining the initial bow using several members, I activate the option reference to list of members. Then I select the appropriate members. Here I define 1, 2, 3, apply and next. Here you see the generated imperfection. Here I change the imperfection direction. Next member is 4. Next member is 5 to 6. Seven to 8. 9 to 10. 11 to 12. 13 to 15. 16 to 18. 19 to 20. 21 to 22. 23 to 24. 25 to 26. 27 to 29. Now I copy these imperfections in down aisle direction. For this, I cancel the visibility node. I don't want to show the numbering, and now I select the imperfections that I want to copy. Then I choose here copy, create copy to
2 copies, and then I have to select the displacement vector in the graphics, and here I choose these nodes, and then I click on OK. I will copy these imperfections with a mirroring. So I choose here mirror, create copy in plane YZ, and then I have to choose the point. I choose this point, and then I click on OK. For the initial bow and Y, I create an additional imperfection case. So here I create a new imperfection case, initial bow Y from imperfection type local imperfection. And first I define a visibility. Here I choose the uprights, visibility by selected and related objects, and I want to see the numbering, and for the down aisle direction the length is the distance between the beams, so the distance between these beams. And I create a new member imperfection for this, so here new member imperfection from imperfection type initial bow, manually relative, same initial bow as for the X direction, also in global and imperfection direction is now Y, and here I have also to activate this option. And then I define the member 1 to 2, 3 to 5, 6 to 7, 8 to 9, 10 to 11, 12 to 15, 17 to 16, 18 to 19, 20 to 21, 22 to 23, 24 to 25, 26 to 29, now I copy these imperfection again. For this I cancel the visibility mode, don't show the numbering. Then I select the initial bow imperfections to be copied. Then I create the copy, and then I will do the same by mirroring. I would now like to combine the imperfections with each other. according to EN 15512, imperfections do not need to be considered simultaneously in down aisle and cross aisle directions. And for the combination of imperfections, I create a group of imperfection cases. So I go here to imperfection case, new imperfection case. I choose here the imperfection type, group of imperfection cases. Here the inclination plus x is to be combined with the initial bow x. So I define a name EC1 plus EC3, go to tab group of imperfection and choose here EC1, add a new imperfection case with operator and here choose initial bow and x. Then I create a new imperfection from type group of imperfection, here EC2 plus EC4. I choose here initial sway and y, choose the operator and, choose the initial bow and y, and I want to create also a group of imperfections, initial sway plus x minus initial bow in x. For this I copy this group of imperfections and then I change here the name and I change here the factor to -1. I do the same here. So that the individual imperfections are not taken into account in the combinatorics, I deactivate for them the checkbox active and then I click on OK. The combination of load cases should be in accordance with EN 15512. I go to the base data. Here I've already chosen that I want to classify my load cases, and for the classification I have chosen already the standard group of EN 15512. Okay. I then create a new combination wizard because I want to automatically create my load combinations. For this I choose here the new load combination wizard. I want to create load combinations, so I check this option and I want to generate load combinations according to second order analysis, and I also want to consider my imperfection cases in the load combination, so I activate the corresponding checkbox and click here on OK. Then I go to the load cases and combinations. Here the standard for combination wizard and classification is taken from the base data dialog, and it's important that here the checkbox combination wizard is activated for the automatic generation of load combinations. Then I go to the tab design situation. Here two design situations are already created. This is the design situation for all variable actions and for one variable actions. If you want to see information about combination rules, you can click on this button. so that the combinations are automatically generated, I have to assign to the design situation a combination wizard, and I choose here the combination wizard I've created before. Then I go here to the action combinations. Here the action combination 5 is the same like the action combination 1, so I deactivate this, and then I go to the load combination, and the load combinations are generated, and you see here for CO1 the group of imperfection 5 is considered, CO2 the group of imperfection 6, and so on. Then click here on OK. Then I activate the steel design add-on for my design in the base data. I go here to the add-ons, activate this checkbox steel design, then I go to the standards, and here I choose the desired standard. Here I want to do the design according Eurocode 3, so I choose here Eurocode 3, and we have several national annexes implemented, and I choose here this national annex. Then I click on OK. Then I go to the steel design settings, and I want to look into the ultimate configuration. I open it, and in the ultimate configuration I deactivate the checkbox perform stability analysis, since all stability effects are already included in the calculation. Therefore only cross-section checks have to be carried out, but with a safety factor gamma M1 for stability design. That's why I activate here this checkbox. Steel design derives from the manufacturing type, whether the design must be carried out according to Eurocode 3 Part 1.1 or Eurocode 3 Part 1.3 for cold form cross sections. However, by deactivating here this checkbox, I can enforce that the design according to Eurocode 3 Part 1.1 is also carried out for cold formed cross section, but I want to do the design according to the cold form standard, so I activate this checkbox again. Chapter 3.2.2 allows the use of an increased average yield strength due to cold working. You can select here the forming factor in the list required here for the calculation. However, the increased yield strength is only determined for cross sections from the database. I click here now on OK. In order to design the member sets and not the individual members, I have to activate the design properties for the member sets. So I go here to the member sets. I select all my member sets and I activate the design properties for them. Okay. And you can see if you go into the member of the member set that this member is designed via the parent member set. Okay, then I go to the table steel design and to the design situation. Here assign the design situation type permanent and transient, and I don't want to design the design situation one, so I deactivate this checkbox, and here I only want to design the load combination 18. Then I go to the objects to design. I don't want to design the members. I only want to design member sets, but not all of them. I only want to design the member set number 7. So I choose this and then I start the calculation. Now the internal forces are calculated, and then the effective cross-section in steel design will be calculated, and then the design will be carried out. Okay, now I see the design check ratio here on this table. If I want to see the details, I have to double click on this to open the design check details, and now 3 effective sections are calculated. These are the effective cross-section for pure axial force, for pure major axis bending, and for pure minor axis bending. If you want to see the details of the calculation, you can here see them. And also you can see the effective section properties. The additional bending moment resulting from the shift of the centroid is also calculated. You can see this moment here in the design internal forces. The effect of distortional buckling is also considered. It's determined using the eigenvalue method, and you can display the mode shape in the cross-section information. I will show you this. I open now here the information about this cross-section, and here you have the possibility to choose the buckling shape for pure axial force or for pure major axis bending or pure minor axis bending. I choose here the buckling shape for pure axial force, and by default the mode shape for distortional buckling with the associated critical load factor here is displayed first, but by clicking on the points in the graphic, further forms of instability can be displayed. It's also possible to display the stresses graphically. To do this, I open the window Result Diagrams and Sections. It's possible to display stresses here on the gross section, and it's also possible to display the effective section with the stresses on the effective section due to axial force and bending moment. I will do this here for the axial force. The effective cross-section is not much smaller than the gross cross-section because of the stiffness, but if you zoom in into this graphic, you can see a small reduction of the thickness. That brings me to the end of the webinar. I hope it helps you in designing cold form cross-sections in steel design. I now give the floor back to Andreas.
Okay, Sonja, thank you for this nice presentation. Yeah, if it was too quickly for you, you can find the recording on our website in the next days. I will show you where you can find that. But before I will do that, I show you only one slide. Just a moment. If you want to get product presentation, a free product presentation, or you want to get a not binding offer, just contact our sales team with that link here, or you can scan the QR code. You will find the PowerPoint slide also on our website. Just a moment, I will show you where you can find it. Dlubal.com is our website. Then under News and Events, you can find our webinars. That's today's webinar, and there are also the upcoming webinars of the next weeks. If I click on today's webinar, in the next days, you will find the recording here in the middle, and you can already find the presentation slides here, the DXF file, and the models here, the RSECTION model and the RFEM model. And you can go through the webinar again with the recording and the models. Okay, that should be also all from my side. Thank you for your attention. Thanks to Sonja for the presentation and Walter for his help answering your questions. I wish all a nice rest of the day. Maybe we meet each other in a future webinar. Maybe a last hint, when you leave the webinar, there's a small survey. Only 6 questions. You can score us or score the webinar. Just note that the worst score is 1, the best score is 5. And you can enter wishes for future webinars and so on. If you don't have any wish, you can leave the field empty or enter any sign. Yeah, that would be very nice. Okay, bye-bye.